So we're going to pick up where we left off at the end of the last presentation, where we started. If we want to go way, way, way back, just as a reminder, geologists had looked at good maps of the Earth and said, "Hey, we think the continents fit together." They said there is definitely a geologic picture that makes a lot of sense if you put things together. So, but they were stumped by what's going on in the Atlantic Ocean. Like, if the continents used to be together, what happened? How did they get to their present positions? They had some ideas, but there's a lot of uncertainty there. And so we get to World War II, where research shuts down, but data is still being collected. Um, the Navy is looking for submarines. They do that with sonar, they do that with magnetometers. And in the end, once we go through the late 40s and into the 1950s, we start to develop a really good picture of the ocean floor. And some of the things that really stood out was in the middle of the Atlantic Ocean, there's a feature that we call the Midocean Ridge. And you can actually follow this ridge not just down the middle of the Atlantic Ocean, but it actually tracks over into the Indian Ocean, and there's a similar ridge in the Pacific Ocean. So they're not all right in the middle of the ocean basin, but they have a very similar form. You'll notice they're kind of rough on the sides. They reach this peak in the middle. And if you look very carefully at this drawing, one of the things you might notice is there's like a little crack that runs down the center of that ridge. And then as you move away from the ridge, it gets smooth. So that brought up a lot of interesting questions. Let's learn more about the ocean floor and see where it leads us. I also mentioned that there was magnetometer data. So one of the problems with detecting submarines using sonar is that you have to emit a sound. So you're basically shouting out your location. Using a magnetometer is a quiet way to do the same thing. A submarine is a large hunk of metal, and so a magnetometer detects the Earth's magnetic field. And if it detects something unusual in the magnetic field, we would call that an anomaly. And so after the war, some researchers sat down with the data that was collected by ships going back and forth many, many times across the Atlantic Ocean with their magnetometers on. And one of the interesting things that they noticed was that as you cross the ocean floor, you detect a series of positive and negative magnetic anomalies. These are places where the magnetic field you get or detect is either stronger or weaker than you would expect. Now, the really interesting thing about these anomalies that they were detecting is that with the mid-ocean ridge at the middle, which is right here where I have my cursor, and where they have present and number 1 labeled in the middle and lower diagrams here, you get a strong positive anomaly. And as you move away from the mid-ocean ridge in either direction, you get these series of positive and negative anomalies that are roughly a mirror image of each other. Very interesting and curious that you would have that. It turns out that if you do another transit in a different location, so if you cross the mid-ocean ridge in a different place, you get the same pattern. Now, what this suggested to the geologists was if the rocks have the same magnetic signature, maybe they're the same age. So this is a way that we could potentially correlate large portions of the ocean floor in terms of age. And the way that you can confirm this or prove it to be incorrect is to collect some samples and send them to the lab and determine the age using radiometric dating techniques. And they did just that. And what they discovered was these magnetic patterns can be used to determine age correlations on large portions of the ocean floor. They also looked at the shape. We talked about the shape of the ocean floor moving away from this mid-ocean ridge, where it's smoother the farther away you get. And it turns out when they started drilling, they discovered that when you're very close to the mid-ocean ridge, the rocks on the ocean floor are a little layer of sediment, and underneath that, the igneous rock basalt. It's a mafic igneous rock. It has a lot of iron in it. That's why it has this magnetic signature, because one of the minerals you find in there is the mineral magnetite. As you move away from the mid-ocean ridge, the sediment layer gets thicker and thicker the farther you get from the mid-ocean ridge. And the basalt is still present, but it's much, much deeper. There's just more material, more sediment on top of that. That suggests that that ocean floor with more sediment on top has been around longer. It's had more time to accumulate sediment. It's just dirtier because it's been there longer. So when we put all this information together, we get a picture that shows us the age of the ocean floor. We use correlation using paleomagnetism. We use radiometric dating, and we can use the thickness of the sediment as well. And here's the picture that we end up with. The mid-ocean ridge is the thick black line. You can see in the Pacific, it's not really in the middle, it's set off to the side. But that mid-ocean ridge is the thick black line. The youngest rocks in the ocean floor are right along the mid-ocean ridge. And as you move farther away from that ridge, the rocks get older and older. Using this information, they developed an idea that they called seafloor spreading. And this explains how you open up the Atlantic Ocean. So this set of slides, which is taken partly from your book, shows you that at the mid-ocean ridge, there's a fracture, and that fracture is a place where the lithosphere is pulling open. And as it opens up, molten rock gets added in to fill in that gap. Now, the reason that there's a crack at the mid-ocean ridge is it's a downdropped area where things are pulling open. And that fracture then gets filled in with mafic igneous rock. It records a geologic magnetic signature, and it then cools and solidifies, and that magnetic signature is then locked into place. The little magnetite crystals are not going to be able to turn anymore once the rock is solid. So we bring that stripe, we solidify it, and then it gets split in half, and one half moves to the right, one half moves to the left, and we continue to fill in the middle, and we make more and more stripes. The older rock is split in half and moves away, and that's what gives us this mirror image pattern on either side of the mid-ocean ridge. So seafloor spreading was really the idea that kind of pushed plate tectonics over the top from a scientific standpoint. So all that work that had been done in the 30s then gets supplemented with this idea of seafloor spreading. And so those are the two really big ideas in plate tectonics. And then we just keep adding on more and more evidence. So we'll go through the rest of the pieces of evidence fairly quickly. In the 1950s, we hit the Cold War. Military again starts collecting data, this time on where nuclear bombs are being tested. They produce seismic waves. So we set up a global seismic network. One of the things we used that to do was see what's inside the Earth. The other thing we did was we started plotting the locations of natural earthquakes because we don't want to mistake a nuclear explosion for a natural earthquake, or vice versa. And so we get this pattern of earthquakes, and you can see they're not randomly scattered around the planet. They're in relatively narrow zones, including along the mid-ocean ridges. We start plotting out the locations of active volcanoes. This activity is in the same narrow zones as the earthquakes, roughly. We start to look at where mountain ranges are. They also tend to line up with places where we would find earthquakes and volcanoes. And we also look for features on the ocean floor like the trenches. You'll notice that's highlighted down here. And those seem to line up with these zones of activity as well. And so the idea is that this geologic activity is focused along the boundaries of our tectonic plates. And so where the plates move into each other or pull apart, we're going to see earthquakes, volcanoes, potentially mountain ranges, and ocean trenches. And so all this geologic activity shows us the boundaries of the plates. So those are all more pieces of evidence to kind of line up and support this idea of plate tectonics. The next piece of evidence that I'll just mention briefly because it was covered in lab exercise number 3 that you probably worked on last week is that there are some hot spots in the mantle. If you are on a plate over the top of a hot spot, that hot spot is going to burn a hole in your plate and create a volcano. If the plates did not move, you'd get one giant volcano. But because the plates do move, the location of that activity stays on the portion of the plate that is over the hot spot. So as the plate moves over the hot spot, we get a chain of volcanoes forming, with the youngest one, the active one, right over the hot spot, and the older ones farther and farther away from the hot spot, giving us kind of a history of where the plate used to be with respect to that hot spot. And finally, probably the last and the biggest and most important and most modern piece of evidence would be that we've actually measured the movement of the plates. This map shows you movements. The original movement measurement took place over plate boundaries. So for example, in California, we could set up stations on either side of the San Andreas Fault and measure the relative movement of the plate on either side of the fault. And then once we get into that happened in the 1960s and 70s. Once we get into the 1990s and early 2000s, we set up global positioning system, GPS stations, and can measure exactly how those stations are moving with respect to the plates. This is a nice global map, and then this map shows you some very specific measurements that have been taken in the western United States. One of the things that this reveals is that when you look in California, the Pacific plate, which is off to the left, is moving fairly quickly to the northwest, and it's actually dragging the edge of North America with it. Once you get into the interior of North America, you can see there's just kind of a slight movement to the west, and then you can see that enhanced drag movement to the northwest due to the contact with the Pacific plate. We'll wrap up by taking a look at what actually makes the plates move, because this was a big question that they had in the 1930s. And this is one picture from your book. You can see these slabs hanging down into the mantle. You can see mantle motion as well. So our understanding today is that the mantle itself convects and moves. That causes the plates to move. And in addition to that, pieces of the plates hanging down into the mantle exert a tug, and parts of the mid-ocean ridge, which sit up a little bit higher, offer a push.